good afternoon to everyone from Southern California. I'm Sifat Muin. I'm a research faculty at University of Southern California at the Civil and Environmental Engineering Department. And today I'm going to present a work that we are doing to validate this physics-based generated ground motions with observed structural responses. More importantly, to see if this simulated ground motion can provide us realistic structural assessments. But before going into the project, I'd like to acknowledge that this work is mostly done by my student, Shun Lai, and my collaborator, Sajjan, who is a PhD student of Dr. Bukanuki. So all the data results are mostly generated by them. So moving on. So we are talking about the engineering applications of ground motion, and from the morning we are saying we do that using response history analysis, linear, nonlinear. So we do that to understand structural performance and also in the design. So ASC 7 has dedicated chapters, chapter 16 or for nonlinear response history analysis, chapter 12 for linear response history analysis to tell us how we need to design it. And we have been saying it from the morning that people do refer to how we can utilize them in design. So just to show, in the current practice, usually there is a target spectrum. It could be a design spectrum or MC level spectrum. We have that target spectrum. And then we go to the recorded databases like the NGFS2 or KickNet or something similar, where we find ground motions and then we either scale them or spectrally match them at different periods or range of periods to find a suitable ground motion suit. And once we have that ground motion suit, we then run the response history analysis and eventually get to our different types of engineering demand parameters. So if it's design, mostly we use interstory drift profiles. We generate the drifts, we look at the mean, and usually when we are designing, we look at the code drift limits, like 2%, 2.5%, depending on the type of structure and use of structure. And then we compare it, and that's how it is used currently in design. However, as we have been it has been mentioned over and over again. The main problem here is the scaling of the ground motions or the spectral matching, and we are changing it. We are changing a realistic ground motion to something unrealistic. And sometimes these unrealistic ground motions it propagates to the structural responses and do give us unrealistic structural responses. So the goal when we are running response history analysis is to simulate the actual behavior. It is to simulate to get reliable prediction of structural demands. So this is where SGMD comes in handy. It does gives us realistic motions. We have been hearing about it. It captures local hazard scenario, and also it provides high spatial resolution, giving us a chance to do site-specific ground motion generation that captures the site geology. So can we use it instead of the generalized ground motions and get a realistic structural performance assessment? So that's the broad question here. And we kind of divided it into two sub questions. One is can we get or generate suits that are closely matching to a target spectrum using this SGMD? So that's one question. And another one is if we want to get structural responses of a specific event, do we really need to simulate that specific event, or can we use ground motions from another event, but in the same region, to get reliable estimates for that event? So these are the main two questions that we were trying to address in this study. So we developed a workflow. It's a three-phase workflow. First, we selected the site that needed to be in the Bay Area region because the simulated SGMD, and also another set that we use is basically located at this Bay Area region. We needed a building that had recorded earthquakes, and then we needed a building that we can have sufficient information to develop a model. So that's first stage. And then we needed to calibrate the model or validate the model, and we used the recorded motions to do so. And here we actually use a new differential evolution optimization method to make sure we have a very good calibrated model in our hand to do the other studies. And then we went ahead to do the validation study, where we used two types of motion. One is from SGMD, the primary one, where we used basically realization 1 to 10 and around 9 stations around our location and site. And then the other one is a simulation, physics-based simulation of Loma Prieta earthquake. So these two suits are used on the calibrated model. We generated the drift profiles, and then we compared it with the ground truth, and we basically tried to find what we are seeing there. So that's how the workflow was developed. Um, so so this is the site that we chose. It is in the region where we have SGMD ground motions available in South San Francisco. It's a 4-story steel moment frame building. It has 11 channels of accelerometer, and it has 6 recorded events that we collected from the SEISMIP database. And for this particular study, we focused on Loma Prieta mainly, and this is because one of the simulated event is Loma Prieta. But another reason is we did find that the HGMD generated motions actually are close to Loma Prieta, and I will show you in the later. So this is why we focused mainly on the Loma Prieta records for this particular case. So we went ahead and started our second phase, which is the model development. We had some information about the building. We knew that it is a moment frame building. We knew that it is built in the 70s. We had the plan view of each floor, layouts of beams and columns. We had the sensors, so we had recordings. However, we didn't have anything else. We didn't have beam column sizes, connection details, floor deck information, foundation information. So that is something we needed to figure out. So here at USC, I teach the steel design course, and my student took that course. So I told her, hey, this is a design problem. Go and do the design. So she basically took it as a project, followed AIC 360 procedures. We know this is not a special moment frame because it was built before 1990s, so in the 70s. So just treated it as an ordinary moment frame. Selected members as per design guidelines, and then ran response history analysis, checked with the recorded motion. If there's a good match, then we say it's a good match. If not, uh, we used for this process OpenSys Pi. And I love the current Gen AI tools because it makes modeling way faster than it was before. So she was able to use different variations of designs that she was getting, and trying to see what is the whether or not we are getting close to the recorded motions. So the model is now can be developed easily, but validation is another thing. And we realized that doing it manually takes a lot of effort. So we actually developed a different workflow to make sure that we can optimize our model. I can give another 20-minute talk on that. I won't. Just to be brief here, we start with the designed version. Then we do our differential evolution algorithm, where we basically scale some of the design parameters. And try to optimize those parameters to match the ground truth that we have, and then check the error. So initially we started with 12% error, and then eventually we went down to 2.2% error. And the final model, which actually is close to what has been designed initially, with the sizes that a structural engineer would basically assign them. So it is close to them, those sizes, and eventually we were able to get very good calibration or a calibrated model with low error. As you can see here, the main error comes from the period, but when it comes to drift and acceleration, we do have very good match here. So once we have the calibrated model, then we went ahead with using this model. So as input motions, we used SGMD data. So here you can see in the red star, the site location, and we used these 9 different stations and the input motions from there as our inputs. And we looked at realizations 1 to 10. So far, we do plan to look at other realizations as well. So we do see variability from realization to realization and station to station also, because the site condition changes, the velocity model changes for each of the stations. The second suite or second type of input motion was from a physics-based simulation of the Loma Prieta event. And it was done by a surgeon who is Dr. Bukanuke's student, and he used this rupture model uh, developed by Dr. Pitarka. And so far there, they basically use the physics-based motion, physics-based simulation to generate motion at these locations where Loma Prieta was also recorded. And then they looked at the residuals and saw that it has a good match. He did actually 2 types of simulation. One is a 1D simulation, and another is a 3D fibers simulation. And we used the input motion from both of these in our study. So here is the 2 sites where we use the input motions from this particular physics-based simulation, which you can see very close to our site. Okay, so this is what I was talking about, why we use Loma Prieta. So here we see the response spectra of Loma Prieta, which we say as the target, the recorded one, in red. And then the black is the mean of realization 1. So definitely SGMD is giving us realistic responses because it is matching with something that has been recorded. So that's good. Now, the question is whether these realistic responses are also giving us realistic, realistic input motions are also giving us realistic responses. So, so these are the actual waveforms of the station 1 to 9 from realization 1. And the red up at the top is the recorded Loma Prieta motion. And we see that there are some stations that are giving us good match in terms of PGA. So stations 3 and 4 in X direction and stations 7 and 9 in Y direction is giving us good match. So this is SGMD realization 1. This is the simulated Loma Prieta. So here you see the response spectrum. Red again is the target. The purple and blue are the 1D simulation. The green ones are the 3D simulations. The one that is below, that is at the rock site. And the one at the top is at the soft site. And we do see it is close to the target Loma Prieta. However, when it comes to PGA, the 1Ds were actually giving us closer value. The 2Ds, the 3Ds were actually over predicting in X direction and under in Y direction. Okay, now to the results. So I'm only showing the interstory drift or the drift profiles here, the results of those. So here you see for story and the drift ratios in percent. The red one is the observed Loma Prieta that we generate from our model, and then the other ones also using the model, the drift profiles from different stations 1 to 9. And then here, the green here, this is from Loma Prieta 3D. And then the purple and the orange here is also 3D on rock site, and the purple is the Loma Prieta simulated 1D. So for realization 1, we see that even though the mean was close to the target, it is still under predicting the observed drift profile. PGA match, the stations that match does not actually translate to interstory drift match. And when it comes to Loma Prieta simulation, we saw that the soft soil site is over predicting and the hard soil is under predicting. And 1D is closer to the mean. Now, this is another of the realization. So this is from realization 10. Again, close match to target, and this time close match near the fundamental periods. And here we see station 4 and station 3 gives us good PGA match. But when we go to the results, the drift profile, we see that the mean actually gives us very good estimate of the actual recorded values. And here, the main finding that we are seeing is it is the spectral match at the fundamental periods that is being the driving force here. And to answer our second question, which is if we want, let's say for Loma Prieta responses, do we need Loma Prieta simulation? Well, the answer is not really. We can use for, the SGMD simulation from the same region to generate spectral matches. We also looked at some other aspects of it. For example, we looked at the other realizations and how closely they match and whether or not. Okay, I'll be very quick.
No, please continue. Yeah.
Okay, so there are two findings from here. One is like when we are talking about site specific, how do we choose the stations, right? When we are trying to select ground motion, is it just proximity or something else? So we saw that the stations that predict well are not always the same for different realizations. They are different, so we want to investigate further what is driving that. Another one is there are some that are always under predicting, so not doing well. So what do we need to do to make sure those are always rejected? Another thing is that, like if we look at R4 and R6, they are close, kind of similar, but when it's giving prediction, they are not same. So other than spectral value, there are other things that we think are basically um, contributing here, and we want to investigate them further, different GM features. Right now, we did look at PGV, PGA, PGD, significant durations. We are yet to find anything, any specific pattern, but we are looking. But when it comes to spectral matching, definitely near the fundamental periods, if we can match them from the SGMD, it is going to give us good estimates. So to end the key conclusion, we can use SGMD to get realistic structural responses. It is opening up a very good paradigm for us, very good space for us to do structural assessment. We need to make sure they are close to fundamental periods when we are doing the spectral matching. Um, and we also need to do further investigation to understand what we mean by site specific, right? Like how do we define it? Is it proximity? Is it geology, or something else here is driving? So we will look at those in our future studies, and eventually we want to develop a systematic criteria for selecting representative ground motion from such simulated databases. So that's it. Thank you.